of this semester, and I will continue what we talked about last semester on quantum field theory. Uh, I'll give you a list about what I'm going to talk about and plan to talk about in this semester in an email instead of using the time of my video. Okay, so please pay attention. Then today I would like to talk about especially the Fermi Golden Rule and how we calculate decay rate and scattering cross section. It's actually not a very complicated issue. However, it is almost everybody covered it. Every textbook cover it. However, sometimes it's not it's not put in very detailed form. Therefore, however, the physics is not that complicated. Therefore, I would like to spend one class on this topic, one lecture on this topic. Let me remind you what we have covered last semester. At the end of the semester of our last class, we have calculated the transition amplitude, which is essentially this. That is a particle in we calculated the amplitude for a particle psi in the far past evolve into a we calculated the amplitude for a state psi evolving into the state of phi, and it is customary to write this transition amplitude. This is called transition amplitude because the particle system transits from psi into phi. However, don't be confused that the psi can only evolve into phi, because actually because it's in quantum mechanics, therefore the destination of this psi in the far future is actually a very complicated state. Okay, and then so therefore the evolution could evolve into various different situation, various different kinds of particles. Okay, however, this transition amplitude capture the amplitude for psi to go into a specific state of phi. But it is customary to write this in terms of a matrix, which we essentially is the evolution time evolution operator from the minus infinity time to the positive infinite time, and this is usually written as S. So therefore, all the information of quantum field theory is actually stored in this operator. And then if you sandwich this operator between a specific past state and a specific future state, then you get the transition amplitude between them. For example, here, last time we talk about how the transition amplitude for a particle A decaying into a particle B plus a particle C, then this transition amplitude will be S, sandwiched between an A state in the past, far past, and a BC state in the far future. Okay, so it is clear from our transparency here. Sorry, I should put it into full screen mode. Okay, forgot. Okay, so this is the we call it transition amplitude, and if you watch what we do, well, what we did this time, the S could actually be solved perturbatively. Perturbatively means it's not solved exactly. However, we can do it term by term in powers of the small parameter in the interaction Lagrangian or interaction Hamiltonian. For example, here is a transparency for the leading order. The U1, the U to a leading order is actually the time integral of the interaction Hamiltonian. from t0 to t. So if you send t0 to infinite minus infinity and t to positive infinity, then you get the s to the leading term. And then if you plug in the field operator into the Lagrangian, the leading term will look like this. And last time I show you how this will act out to calculate. How this form could be acted on to calculate the transition amplitude. It's almost like a motion picture. So you put in A, and you put in B, you put in C. And therefore, essentially, it is a annihilation operator plus a creation operator, annihilation operator, creation operator, annihilation operator, creation operator. Therefore, you need the right combination so that you need the right combination to get a non-zero matrix element. That's the essence of the Feynman rule and our calculation of the amplitude. So I will not go back to review the whole thing. You can follow the transparency, and of course I think Professor Chen has already covered this part. But I just like to remind you with a very, very simple fact. I think we go too fast last time. That is, when you choose the right combination, and don't forget these combination, the annihilation operator and creation operator, comes from the A operator, the field operator, A and B and C. And inside this field operator, in addition to the annihilation operator, there's the exponential term, which we usually call it a plane wave solution. Of course, this is not really a wave, so it's a particle thing. Then there is an exponential minus px. So we will have an exponential factor here, exponential factor here, and exponential factor here. So, and these exponential factors are all related to x. So essentially you have an integral, a four-dimensional integral, space-time integral of a exponential factor altogether. And it's easy to observe that. And in front of the x, you have a p1 minus p1 minus p2 minus p3. So this integration could be done explicitly. Okay, it could be pulled out. Sorry, you could be pulled out from the calculation and calculated explicitly. And the calculation is obvious. It is equal to the delta function of p1 minus p2 minus p3. Of course, it's a four-dimensional. There are four delta functions, one for each component of the four momentum. Okay, and we usually call it the momentum conservation, because it stated or dictated that P1 must be equal to P2 and plus P3. That's momentum conservation. Very easy and simple. So this is a very simple illustration that a delta function of momentum conservation will appear in the transition amplitude in this calculation. And it's actually happened everywhere. In every diagram, this is only the leading diagram, right? And in Feynman, in terms of diagram, it's only this. However, you can go to proof this explicitly. You can prove it in general. The delta function will appear in any diagram in your calculation. Of course, it's not a surprise because momentum conservation is an old friend who has been with us for so long. Okay, so yeah, so the delta function appear in our calculation. Don't be surprised. However, it poses a very serious problem when we try to calculate the real observables. Okay, so let's move on. That's a very small, quick review about relevant factors. Of course, here I also calculate the scattering amplitude of AA to BB, and the same thing happened after you do the right. No, this is propagator. I'll cover it next time. Okay, so here, sorry. Again, in this scattering amplitude, scattering process calculation, you also have an exponential factor, exponential factor, exponential factor, exponential factor. If you find the right combination to fit the matrix element. Okay, so again, after you integrate the out x1 and x2, you will get a exponential function. You'll get a delta function. The same thing. Okay, so that's what I'm trying to convey with this very short review. Okay, now let's move on to another issue. Let me quickly review what we really observe in laboratory. In observatory, the observables contains mostly two quantities. First, decay rates. Second, scattering cross section. They are not all. There are other observable to be observed. However, these two quantities are the most important quantities and easy to describe and calculate. First, decay rates. Decay rates here, it is defined as the probability of decays happening per unit time. Remember that the decay is an uncertain quantum process. Therefore, we can only calculate and predict the probability for it to happen. And of course, it can happen anytime. Therefore, we can only calculate or predict the probability or the rate of the decay happening. Therefore, that's why here you can see that this is the probability of decays happening per unit time. So that's why this is called decay rate. And usually the notation for decay rate is gamma. Okay, so and the unit is, remember, it's probability. There's no unit, but per unit time, so it's divided by time. Therefore, the unit is inverse time. Remember, inverse time is equivalent to, in the natural unit system, is equivalent to energy, and energy is equivalent to mass. Therefore, this the gamma actually has the same unit as energy. Okay. Then a key observation is that this decay rate usually is independent of time. Therefore, you can, except for in the early universe. In the early universe, all the decay rate could depend on how many particles there are in your system, and therefore, this decay rate, if this decay rate is a constant, then you can easily calculate that. You can easily calculate the number of the particle. Okay, because the change of the change of the rate of the particle is proportional to n itself, with the proportional constant equal to gamma. Therefore, it's the famous rule of exponential decrease for a decaying process. So it's very natural. So gamma is the decay rate is the first observable we usually calculate and predict and do experiment in particle physics. And secondly, a huge number of experiments is about collision. That is, we collide two particles. At first, we hit the particle with a fixed target, or we hit the fixed target with particle. However, when our experimental skill becomes better and better, we now can hit two flying particle, like you hit two bullets. And the key observation is that the number for this collision to happen is proportional to the intensity of the particle beam. When I talk about intensity of particle beam, I mean the flux, or in the even more technical term, it's called luminosity, L. Okay, and essentially it's flux. The definition of flux is the number of incoming particle per unit area per unit time first, and then per unit area. Okay, so that means if you squeeze the particle you squeeze the particle, then you increase the luminosity. Yeah, it's obvious because if you, yeah, so and that means if when you squeeze the particle, then per unit area you get more particle into the same unit area. So that's why the luminosity becomes larger and larger, and in terms of light, it becomes more and more intense. Okay, so this is luminosity. And it's obvious to observe that the number for this collision to happen is proportional to L, luminosity. For the simple reason that the more particle you squeeze into an area, then the more possibility it will hit the other particle, and for this reaction to happen. Therefore, dn is proportional to L, obviously. Okay, and the point is, if dn, the event rate for collision to happen, is proportional to the luminosity, that means the more intense of your beam, the more for the event to happen. However, if you divide the event rate with L, then the result is the proportional constant. When I say it's a constant, that means it's independent of the strength of the beam, as I say here. This d sigma is independent of the strength of the beam. That means this d sigma will be the same whether you do an experiment at LHC, a very advanced experiment, or you do it in somewhere else with a much weaker beam. So therefore, again, dn depends on the machine. However, d sigma does not depend on the machine. When you divide out the luminosity, then this d sigma you get is actually independent of the machine you do. Therefore, it is an intrinsic quantity which we can calculate and can be used anywhere you like. Okay, and second, please observe that this quantity we define, d sigma, has an unit of area. It's obvious because n has no unit, but L is 1 over area because, oh sorry, this dn is 1 over t, okay, and L is 1 over area over t times t. Then therefore the time, the unit of time cancels out, and reverse the order, the unit of d sigma is area. So we usually call it scattering cross-section. Cross-section means the area for particle to pass. Therefore, that's why this d sigma is called cross-section. And this name has a history. In the old thinking, I mean, old means in the 1900s, before the quantum mechanics was invented, this d sigma is actually a cross-section. Okay, so if you think of the scattering experiment of bullets instead of particle, then the particle, when it hit a target, then it will be scattered like this. That's how this scattering name comes from. And it is easy to see that the scattering angle has a 1-to-1 correspondence with the impact parameter, that is the perpendicular distance of the particle trajectory with the scattering center. If there is, as I show you here in this graph, and if they have the same 1-to-1 correspondence, then you can calculate the number of the scattering into a certain angle by how many particles you pass through a certain area. Okay, so and in this way, the number happening is indeed luminosity, again flux, times the cross-section passing through this small circle, or passing this small ring, not circle, the ring. That again, those passing through this ring will be scattered into this scattering angle. Therefore, if you want to know how many particles will scatter into this angle, then you calculate how many particles you pass in through this ring. And therefore, the number of particles is obviously the luminosity or flux times the area of this ring. So in this case, you can see exactly the same equation as I have shown you, and but totally different the fundamentals of physics. So, but exactly the same. And here, in classically, this d sigma is indeed a cross section, an area for the particle to pass through. Okay, so the same formula apply classically and quantum mechanically. Okay, and please remember, of course, after I told you the origin of this name, I have to remind you that this picture only happened classically. That means it only happens to bullets. Okay, not to particles. Particle is not bullet, as you have already known very clearly from quantum mechanics course. So particles, at least you need a wave picture. Okay, so therefore don't be confused by this classical picture and the more advanced quantum field theory description of a scattering process. Okay, then so that means in quantum mechanics, in particle physics, you no longer can write a path or trajectory of the particle flying in space. You can only say that when you inject a beam, a particle with luminosity or flux L, then you can detect the particle at different scattering angle and different scattering products. And you will observe that, again, this number is proportional to luminosity. And you divide the two, you got something. This something is independent of the luminosity and could be calculated. It is intrinsic. Okay. The unit of the d sigma is area, but it doesn't mean it's really an area. Okay. So, but anyway, dn over L, cross section. Oh, we'll call it cross section. So now we have two quantity. Let me remind you again: decay rate and scattering cross section. These are the observables we do in particle physics most of the time. And well, I know how to calculate. I have shown you how to calculate amplitude. However, these observables are not amplitude. These observables are about probability, or the square or absolute value square of the amplitude. So that's intrinsically what we want to talk about today, how to go from amplitude to probability. We know how to calculate amplitude, but how about probability? We know how to calculate amplitude, but how about probability? This is I follow very closely the lecture notes of Tom. Okay, I will send you again through email and listed on the course webpage. And this is 3.6. As he say here, what we measure, cross-section, decay rate, they are all about probability. That's the key. The thing we can observe are probabilities. However, the thing we can calculate is amplitude. Well, you say, why not? We just square it. The point is, there is a delta function. So here, Tom say, one small subtlety here is that the S matrix element all come with the factor of delta function, as I have shown you in the beginning of our lecture today. So we'll end up with the square of a delta function. Well, what is it? We know what delta function is, but we don't know how to take care of the square of delta function. Okay, so that's a that's not a big problem. However, it's a very significant problem. People in before World War II spent a little bit of time to take care of. That's why, especially Fermi. So that's why how to take care of this square of delta function is what Fermi taught us. Therefore, it is coined a name, Fermi Golden Rule. Okay, the key is that, let me put this simply and then we'll elaborate on this. The key is that when you square delta function, see, I show here, then you get a delta function times time. Time means the whole stretch of time you do experiment. And when you extend this time to infinity, then you got a problem. That's why we say there is a problem of square of delta function. However, it's not a real problem because in experiment we do not really observe the experiment for infinite number for infinite time. We usually do it because the two particle or decay could only happen during the time the experiment is performed. Okay, therefore, and the collision actually happened very short, in a very short time. Okay, so the number we really calculate. Oh yeah, and remember that we say it's decay rate or cross section. They are all event rate per unit time, and therefore that means here we got a T, capital T. Usually the real thing we calculate or observe is the quantity, the probability per unit time, and therefore this T will be canceled out. Therefore, when we calculate, we don't really get a square of delta function. We get a one delta function only if we take decay rate. We can take time rate. So that's the essence of the Fermi Golden Rule. So it's quite simple. Okay, so Tom here observed that as we will now see, this comes from the fact we are working in an infinite space-time. And therefore, if you divide it by time, divided by space, you get a finite number. That's the key. Okay, so let me illustrate the whole thing, the Fermi Golden Rule, and how it applied in quantum field theory in the next about 20 minutes. First, let me remind you and set it as an example, the calculation of U or S to the leading order. Okay, so it's we have already mentioned. This is the S or U in the leading order. It is actually a time integral. Sorry. Sorry, I'm fine. Okay, so this is the leading order of S, or leading order of the time evolution. It's the integral of the interaction Hamiltonian. This is also true, but please observe that this is also true in quantum mechanics. Actually, I first run into this theorem, so-called Dyson expression in quantum mechanics, under the name of time-dependent perturbation. Time-dependent perturbation. So if you want to consult your quantum mechanics course, sorry. If you want to consult your quantum mechanics textbook, it's under the title of time-dependent perturbation. Okay, so let me start with illustrating the whole thing in quantum mechanics. The point is, in quantum mechanics, the transition amplitude, actually, if you calculate the same kind of transition amplitude, but in quantum mechanics, you also get a delta function, which is the delta function of energy. Okay, let me illustrate it more clearly. Here, if I calculate if I calculate if I choose two energy eigenstate. When I say energy eigenstate, I mean the energy eigenstate. I mean the eigenstate of H0, the free Hamiltonian. Okay, so H0 n is equal to En n. And therefore, if I want to, I assume that in the far past and in the far future, the interaction will die out. This is very important approximation I will talk about maybe next time. We call it adiabatic approximation. Again, in the far past and in the far future, the interaction will die out, could be ignored. Therefore, in the far future and in the far past, particle exists in eigenstate of the free Hamiltonian. And then I can ask how a particle a state n in the far past will evolve into a state m in the far future. And we sandwich the time evolution operator between n and m. Here I haven't sent the time to infinity, so it is actually an evolution from 0 to t. And then it's easy to see that from our earlier transparency, this u to the leading order will be this time integral. And this hi is the interaction picture, interaction Hamiltonian. And it could be related to the Schrodinger Hamiltonian, Schrodinger interaction Hamiltonian. Remember, in Schrodinger picture, the operator is time independent. So this h does not have time dependence. Therefore, all the time dependence has been extracted out to the exponential factor in front and exponential at the back. And therefore, if you plug in this into here, and observing that this n is an eigenstate of h0, then this exponential factor becomes a numerical factor. It could be taken out. And what remains is the Schrodinger picture interaction Hamiltonian, and it is time independent. Therefore, the matrix element in front is time independent. And all the time dependent quantity integration we need to calculate could be summarized at the back. And this, of course, is easy to calculate. I will leave it to your exercise. And this factor could will become this exponential I omega t minus 1 over omega. I forgot to say, this omega is the energy difference between m and n. So that is defined as em minus en. Okay, so this gives you the probability for the transition from n to m. Okay. And so when you square it, you say, well, where is the delta function? Yep, there's no delta function yet because the time is not infinity. So, but if you square it, then this factor could be calculated to give you this function, 1 minus cosine omega t over omega squared. Try it. And then this function has been depicted here in figure 19, and you can easily observe actually it has a maximum at the horizontal axis are omega. Horizontal axis is omega, and therefore you can see this function has a peak at omega equal to 0. That's why it resembles a delta function, but not yet. Okay. So, but we know that, and another way to say it is a delta function is that you need to try to do it yourself. I haven't. Again, leave it to your exercise, and you will see that this peak actually has a width, and this width is equal. Here, Tong write it as delta E, the width, and this width is equal to 2 pi over t. So that means when t goes to infinity, then delta E, the width of the peak, will vanish. But, however, the integration of the whole function, that is the area below the curve, is actually pi equal to t. Therefore, it actually becomes infinity. That's why this is a delta function, because it is a delta function times pi times t. Okay, so therefore this function showed you that when you observe this transition long enough, a particle can only go to somewhere which has the same energy as originally. Okay, so however, of course, you can go back to say that if you you didn't observe the time long enough, for example, this t is not equal to infinity, then it is allowed for the particle to not observe the energy conservation for a certain amount of delta E. So it is sometimes called the uncertainty principle of energy, because U times delta E times T is equal to 2 pi. The smaller time T you observe, the larger delta E, uncertainty of energy, you are allowed. However, when T goes into infinity, that means you observe the experiment long enough, delta E must be equal to 0. Okay, so it's sometimes called uncertainty of energy and time. But anyway, for us, the probability of the transition is proportional to delta omega when time goes to infinity. And therefore, I can write it in several different ways. Here, Hong write it as when t integrate. Let me say this first. Then, therefore, when t goes to infinity, this transition amplitude is equal to 2 pi times t times this matrix element from here. The matrix element times square times delta function of omega. Delta function of omega. Okay. So it shows you that if you are careful enough, then and then if you take the time derivative, you ask the transition that will happen per unit time, then you take the derivative of this Pn, then you arrive at this quantity which is independent of t. So here, when you send t to infinity, you are safe. There's nothing wrong here. Okay, that's why from here to here, taking the time derivative, then you got the one delta function instead of two. That's the essence of the message I want to convey today. Okay, again, the key is that if you calculate, so essentially, the time evolution here, Tong put it in another way. When you calculate the transition amplitude, and here I'm more careful about the time to keep it finite until the very end. So Tong say if you send time to infinity after you calculate the amplitude at the level of amplitude, then the amplitude has a delta function. So that's why naively you will get the transition probability of delta square. So I say this is the essence of the problem today. However, delta square is equal to delta times capital T. If you keep the time to a finite number. And then if you calculate the transition probability per unit time, then you recover that the delta function is only the first order. Okay, so this is called Fermi Golden Rule, this one. Of course, originally, another form to write it is to sum over the transition amplitude for various m, because usually the final state is part of a continuum. Then therefore, the thing you observe is usually a integration of this transition amplitude over a range of energy, as I say here, DEM, with a certain weight, or sometimes called density of state, ρ. Okay, so if you integrate the whole thing, and as I say, this is a delta function. Then after the integration, this delta function will enforce a time energy energy conservation in your result. So let me follow Tong's description. This equation gives a constant probability for a transition per unit time for states around the same energy. Okay, so En will be approximately equal to Em with the same value. Okay, and after you divide out take time derivative, then the rate will be this times the energy density, the density of state. So this is the original form of the Fermi Golden Rule. Okay, when it is applied to the quantum mechanics. Okay, so this is Fermi's Golden Rule. So you can see that it's actually very, very simple. It's actually very, very simple. However, you have to take care of it. Otherwise, you'll get a delta function square, which does not make any sense in observation. Okay, so now let me extend this logic to quantum field theory. It is almost the same in quantum field theory that we will have a delta function, and then when you square it, you will have a delta function of energy times, usually it's a 2 delta function. But when you have 2 delta function, the second delta function, the argument of the second delta function will be made immediately equal to 0 by the first delta function. That's what will happen if you have 2 delta function. And remember, the delta function is actually a exponential integration of an exponential function. And that's why when EA minus EB minus EC is equal to 0, then that means this argument is equal to 0, and the exponential function is equal to 1. And after integration, it gives you t, the time duration. Okay, so this is what happened in quantum field theory. You got a actually it's the same as the quantum mechanics version, very similar. Okay, and however, as we know, probability must be larger than 1. So you again to observe that what we observe is actually the rate. That is the probability divided by time, and therefore this t will be canceled out, and the final result of the decay rate will be equal to a delta function times a finite quantity. Okay, so in short, taking time derivative will take away one delta function. That's the key. Okay, however, in quantum field theory, we also contain, the S matrix also contain a 3 momentum conservation. Okay, and as I have shown at the beginning of our lecture today, this S matrix will consist of a delta function of the 4 momentum, that is 4 delta function. So it's customary to take out this delta function, and as I emphasize, it happens at every level, every diagram, every degree. Therefore, it is customary to take out this delta function and define a new matrix element, T, and or sometimes called reduced Lorentz invariant transition matrix, T. Okay. And so it's natural to expect when we square this amplitude, we will get a delta square. But instead of delta square, if you carry out the integration as I did here, then I don't want to go into a formal proof, but it's natural to expect you will get a v times t, just like I will get a t in this earlier derivation. Okay, so if there is a v over t times a delta function, and the capital T has been taken care of, as I say, by the time derivative of the rate, and usually there will, if I define gamma as the probability of decay per unit time per unit volume, then this v will be taken out also. Therefore, again, the result, gamma, will be 1 delta function, not 2. I mean, not square of a delta function, but 4 delta function, each corresponding to 1 component of the 4 momentum times this matrix element, which is finite. So that's the final result, end result. Okay, and very, very similar to the Fermi Golden Rule I have said in the in earlier pages. Okay, but this is not careful enough. Let me try to, it could be done more carefully. This is what Tong did. And now it's familiar to you. I think you have been familiar, you are familiar now how the capital T is taken care of. What remains is how this V is taken care of. It's not mysterious at all, because the problem with the V is because we work in infinite space. And if you work in infinite space, then the I, the state we put in our calculation, that is states with fixed momentum, will have infinite normalization. As you, it's very, very similar to quantum mechanics. In quantum mechanics, state with fixed momentum corresponds to plane wave. And if you calculate the probability of plane wave, then you get the infinite, because the probability density of a plane wave is a constant. So if you allow the space to go to infinity, then you get infinite normalization. Okay, so what we can do is to divide the S matrix we have by the norm, or the magnitude of the state II and FF. Okay, and before we send V to infinity. Okay, eventually we are going to send the space to infinity. However, we keep it when we calculate this guy, and then you will see that the V will cancel out. That's the key observation. Okay, so as I hinted, the magnitude or the normalization of this plane wave state will be proportional to V. It's not difficult to calculate, as I will show you. But first, you have to that's because when you calculate the magnitude of I, then I is created by AP, dagger, the creation operator. Of course, if you are very, very picky, then you could notice that this AP does not have a vector here. Okay, so in our earlier transparency about Feynman rule, it is AP vector, 3 vector. This is a non-Lorentz invariant form of creation operator and annihilation operator. Usually, you need to replace it by multiplying with 2e, square root of 2e, then to get a Lorentz invariant Lorentz invariant creation operator. Okay, and therefore this I, if it is Lorentz invariant, has to be created by the Lorentz invariant creation operator. And therefore we got an extra 2e in front. That's the origin of this vector. Okay, so I let you follow this small factor in the notes. And then this product of AP and AP dagger could be written as the commutator of AP and AP dagger, because if you reverse it, then the annihilation operator will annihilate this vacuum. Therefore, the additional term vanish. And A and A dagger commutator is equal to the delta function of P minus P. But P minus P is equal to 0. So that's why you get a delta 0. Delta 0 means it's a space delta function of 0. Okay, so space at 0, if you go back to the calculation here, remember when you got a 0, then it gives you time. So if it's a space, delta 0 equal to V. So that's why here, actually I have the formula here. So it's a delta function of 0. That means it is a exponential minus I P minus Px integrated over space. And if P minus P is equal to 0, of course, P minus P is equal to 0. So that means this is the argument vanish, and this exponential equal to 1 after integration is the volume, V. Okay, so here is a very, very subtle, a detailed derivation of this V factor. Okay, so the bottom line is the normalization or the magnitude of this I state is equal to 2E times V. So are the magnitude of the final state. We got a 2E times V. Okay, so you put everything together into the formula. The P will be equal to V times T. V comes here, and T comes from and the T comes from the delta function of energy, and A is the transition amplitude magnitude, and this if this particle is at rest at the beginning, the decaying particle is at rest, the 2E will be equal to 2m, I think. Okay, and the V will be here, and the final particle also has a magnitude of 2E times V at the bottom. Okay, so that's the probability we can calculate in decay rate. We can calculate in quantum field theory, and it is easy to observe that this V would be cancelled out with this V, and if you take time derivative, this T will disappear also. Okay, so what remains? So this V disappear, this T disappear. What remains is the final state, 2EP, 2EV. So as Tang says, what remains to be done is to sum over all final state. And when you sum over final state, you need to integrate over D3PF. This should be PF. Okay, I think there is a typo in Tang's notes. So this should be PF. Oh, but maybe this I does not mean initial. It is just the number of the final states. Okay, so for every final particle, you will have a D3pi over 2 pi cube. But this V comes from when you count the phase space. In the phase space of P, there is the density of state is V over 2 pi cube. Okay, so this is familiar. Okay, so if there is a V, if you put in this into your integration, then this V will cancel out the V at the bottom here. So at the end of the day, all the V disappear from your calculation, all the T disappear from your calculation, and then now you can send the space V and the time T to infinity, and still the the decay rate is a finite number. Okay, so that's the key. You can call it you can call this the Fermi Golden Rule in quantum field theory. Okay, that's the final formula. Gamma is equal to 1 over 2m, the sum over all the final state of the transition matrix element square. Nothing serious. Okay, and this phase space is this. Remember, we still have a one delta function and phase space for every final particle. So we usually gather them together and call it the phase space, because it is this factor is going to happen when whatever the reaction is. It's independent of the interaction. Therefore, it's good. So it will appear anyway, whatever interaction it is happening. Therefore, it's easy to gather them together and call it a new name, phase space. This d pi is the phase space. Okay, and it consists of the delta function of the whole momentum and a phase space vector for each final particle. Okay, the n, that's the gamma decay rate. Beautifully. Okay. Now, since time is a little bit up, then I will go very quickly through the cross section, and the notes are in the transparency, so you can follow easily. And in cross section, dn is equal to L dot d sigma, dot dn dot sigma. Therefore, d sigma is equal to dn over d over L. Therefore, in addition to the probability over time, you now have to divide by a Unix, a flux. And the flux is not difficult to calculate. The flux is equal to rho times V. And rho is equal to V minus 1. So that's why Tong write this formula. F is equal to V1 of minus V2. That's the relative speed over V. And if you plug in this L here, then you got this formula. I forgot to mention this 4E1, E2, V comes from the initial state, because now I have two particles. So you have to, this I, in this first derivation, there's only one particle, which is decaying. But now in scattering amplitude, you have two particles. Therefore, you have 2E times V. But one of the V will be here. Okay, so one of the V cancels the V in the calculation, and T again taken care of by the time derivative. You arrive at this expression. And if you plug in F, and you got this. Okay, so it's not difficult if you follow the expression, and it's a bit awkward for me to lecture about it. So please take a look at this derivation. But finally, this is d sigma. This is d sigma, the cross section. And oh yeah, so I have the formula here. And if you are really interested in details, I have some transparency. Probably I won't go into detail here. This I took it from this most recent quantum field theory by Fredkin. Fredkin is a very, very good condensed matter theorist, and he actually advocate to teach quantum field theory to both particle physics and condensed matter theorist. So that's why he call it integrated approach. I'm not very comfortable with that idea, but anyway, this is one of the most recent quantum field theory textbook you can get from market. And actually, he is a very, very good writer. So here I took pages from his this textbook about the scattering amplitude. Why it is good is that here he used the wave packet, because remember in our earlier derivation, I are almost exclusively the plane wave. However, in laboratory, we more or less see particle as a point, and that point, after learning quantum mechanics, you know they are wave packet. Okay, so that means if you want to describe scattering really rigorously, you need to put in a wave packet formalism. Okay, I checked the writer yesterday, since most of you is involved in Professor Chen's course, and I noticed that writer also used a wave packet. So I think this the next several transparency will overlap with Professor Chen's exposition in class. So that's why, but I still listed for your reference. Okay, I think again these should be very, very similar to very similar to writer's exposition. Okay, so the key is this I, the incoming state. now consists of two plane waves, P1, P2, one for each particle. And here he introduced a wave packet wave function F1, P1, F2, P2 to describe really two almost point-like particle colliding. Okay, so that's the interesting thing that you probably want to follow a little bit. Okay, so then everything else is the same. So the probability for this collision to happen will become a formidable expression, but it's not really that difficult. Here is the transition amplitude square, but you now need to times 4 wave packets wave function, one for each particle and one for each incoming, one for each matrix element. Okay, and then he made a very simple approximation that this wave, the matrix element is insensitive to P1, is insensitive to the momentum. Of course, it depends on the momentum, but what he says is not that sensitive, or the spread of the delta P is smaller enough, the spread of the momentum or uncertainty of the momentum is small enough, I can treat it, the matrix element, as a constant in terms of P. Okay, so therefore, this transition amplitude could be replaced by a constant that is independent of the P1 and P2. And then and this then you can carry out, and this formula W, yes, from here to here you probably need to delve into detail. Let me see here. I'm looking for, oh yeah, and here he replaced the Fourier FP by the Fourier transform. So this F tilde X are the wave functions, okay, and therefore you got this, okay, and then if you take the transition property per unit time and volume, then you can see that this expression will equal to this, and then the transition probability per unit time per unit V will be equal to the flux times the this, I think, the density, and times d sigma. Okay, so if you write down the density and write down the, oh sorry, this is the density. Oh, sorry, this is the density, the flux of the incoming particle. Here you assume that the particle 2 is at rest and the particle 1 is moving. So here phi in is the flux of the particle 1, and particle 2 is at rest, but you need to multiply by the density of this particle is in front. Okay, so you relate these two, you get the sigma, an expression for sigma, because you have already the left-hand side, and you have this, then this sigma could be derived. So yeah, okay, so here has some comment and details. You can probably want to consult it. And then with this formula, you can extract d sigma, which is equal to this. Okay, so let me emphasize this sigma is exactly the same what we have earlier with a simpler transparency. Okay, here you can compare the two expressions yourself and easily conclude that this basic formula for the cross section they are totally the same. Here I have a delta function as expected. Then here I have a transition amplitude. I have a transition amplitude from the P1 to the initial state to final state, and square it. And this actual factor comes from, you can check it is the same as the E1, E2 times V1 minus V2. Okay, and here he write it in a more Lorentz invariant form as this. Remember that d sigma is a Lorentz invariant quantity, because when you boost in the direction of the collision line, the collider line, then the cross section is perpendicular to this line, and therefore with the boost in the colliding line, the area does not change. That's why it is a Lorentz invariant quantity. Okay, so that's why you can write the whole the vector in front in terms of a Lorentz invariant form. Okay, and therefore finally this is the d sigma. Okay, this is d sigma. Let me summarize all the things we covered today. We got a formula for decay rate. We also got a formula for cross-section. In this section, there's a phase vector. Phase vectors are listed here. And the transition amplitude is the Lorentz invariant form is related to S, like this. Okay, so usually for practicing particle physics, we usually just concentrate on this transparency and forgot all the derivation until you need to teach your course on quantum field theory. Okay, so yeah, it's fun, but it's usually just forgot it until you teach. So because these final formula are so simple to use, but just remember it actually has a little bit complicated past, and yeah, that's it. Okay, so next time, so we solve the problem of the square delta function square. But next time, I would like to return to the amplitude for a while. Okay, and yeah, so I'll see you next time. Next time, I'll talk a little bit about what we'll encounter when we go back to the amplitude. There are still some problems we need to tackle. Okay, see you next time.